Hey, welcome to chapter 7.3, where we're going to talk about energy changes in chemical reactions. We've already talked about what chemical reactions are, how to balance them to observe the law of conservation of mass, and we've talked about the 5 different types of reactions: synthesis, decomposition, single reaction, or single replacement, double replacement, and combustion reactions. And today we're going to talk about how energy changes occur in those different kinds of reactions. So as a chemical reaction occurs, chemical bonds are broken and then reformed. This has to happen because whatever compounds or elements we start with in the beginning of our reaction end up changing to completely new compounds or elements in the end because of the formation of these different bonds. So an example is when we take propane and oxygen, and the bonds between these things break and then they reform to make carbon dioxide and water. Now, all of these bonds contain what's called chemical energy. Chemical energy is what makes us go. We eat food, and then we break that food down, and as we break the food down, we break the chemical bonds within that food, and then we use that stored chemical energy to run our bodies. Now, the breaking of chemical bonds to take apart the reactants requires energy. We always have to put in a little bit of energy to break the bonds of whatever we start with. And the forming of chemical bonds in the end to make the products produces energy. The forming chemical bonds will always produce a little bit of energy. The thing is, these are not always equal. But if we think about a grill, a gas grill that has propane, we have to ignite that propane with a spark before we can get it to ignite and before we can make that chemical reaction take place. That is putting a little bit of energy in to break the bonds of our reactants, of the propane and the oxygen that we start with. Without that spark, the chemical reaction isn't going to take place because we haven't put in a little bit of energy to break those bonds that we have started with. In the end, however, the production of all of that heat and light that we use to make our delicious cheeseburgers, that comes from the new bonds forming when carbon dioxide and water are formed at the end of our chemical reaction. So, like I said, the amount of energy required to break the reactant bonds is not always equal to the energy produced by making our products. In fact, they are hardly ever equal. And this may mean sometimes we need to put in more energy than we get out, or sometimes we get out more energy than we needed to put in. And we've actually talked about these 2 different kinds of reactions when we talked about physical changes. And they are the same thing. We call them the same thing. The 2 different types of energy transfer are called endothermic and exothermic. So when we talked about physical changes, we talked about an endothermic change as taking energy in, and an exothermic change as giving energy out. For example, endothermic is when heat is being absorbed. Let's say an ice cube is melting. It is absorbing all of the heat energy around it, and as it absorbs that, the temperature of the molecules increases and it goes from a solid state to a liquid state. An exothermic reaction is one that gives off energy. So the opposite of that is when something is freezing. So if we have water in a freezer, it's in the liquid state, and as it cools down, it's giving thermal energy to its surroundings and getting colder and colder, and eventually it will go from the liquid state to the solid state. Now, we can also talk about endothermic and exothermic reactions in terms of chemical reactions. So in an exothermic chemical reaction, energy is released. That means that we get a lot more energy produced from our products than we had to put in the beginning to break our reactant bonds. An example of this, as we've already talked about, is what we call the combustion of propane. So with propane and oxygen, if there is a small spark, that is just a little bit of energy that we put in to break the bonds of propane and the bonds of the oxygen molecules. And in the end, when carbon dioxide forms and when water forms, the formation of these new bonds produces much more energy than we had to put in, and so we get out a whole bunch of heat and light, which can be useful for us if we're using it for a propane grill or, let's say, a heater. The opposite of this is an endothermic chemical reaction, and this is where energy is absorbed. So an example of this is when we have to put in more energy to break our reactant bonds than we get in the end. An example of this is when we decompose mercury oxide. So if we have mercury oxide and we want to make mercury and oxygen gas, we want this compound to separate into its two constituent parts, we actually have to put in a lot of heat. Now, we have to put in all of this heat from this flame in order to break these reactant bonds. And when these new bonds, these oxygen molecules, form in the end, they produce very, very little energy compared to all of the energy we had to put in. So this is called an endothermic reaction. Now, a really important thing to note is that the amount of energy we have before a reaction is always equal to the amount of energy we have after a reaction. It's just like the law of conservation of mass, where we have to have the same amount of an element before and after our chemical reaction. The same thing happens with energy. But what determines whether a reaction is endothermic or exothermic is how much energy is stored within the bonds themselves. So we call this the law of conservation of energy. So if we take a look at how much energy is stored, absorbed, and released in a certain chemical reaction, we can determine whether it's endothermic or exothermic. So remember, a long, long time ago we talked about energy, and our unit for energy is the joule, which we abbreviate as J. So if we have a chemical reaction where there are 20 joules stored in the chemical bonds of the reactants, and they have to take in 2 joules in order to break, and then in the end 8 joules of chemical energy is stored within those bonds, and 14 joules is released into the universe, we can look, and in the beginning of our chemical reaction we have 20 plus 2 is 22 joules total. Now in the end we have 14 plus 18, which is also 22 joules total. So the total amount of energy before and after is exactly the same, and the universe won't let anything else happen. It always has to stay the same. But we would call this an exothermic reaction because we get 14 joules of energy released in the end where we only had to put in 2 joules to begin with. So we get much, much more energy out of the end than we had to put in into the beginning. And the rest of the energy is stored within those chemical bonds. Another example is, let's say we have 10 joules of stored energy in the beginning, and it absorbs 7 joules of energy to break those reactant bonds. And in the end, we have 15 joules of stored energy, and only 2 joules are released. Now, if we look at our totals, we have 10 plus 17 joules, or 7 joules, so we have 17 joules of energy to begin with. 15 plus 2 is also 17 joules of energy. So we start and end with the same amount of energy, always, always, always. But now if we look at how much energy we had to put into the reaction and how much was produced, we had to put in 7 joules in order to break those bonds, and only 2 joules were released. So we would think of this as an endothermic reaction because it took in a lot more energy in the beginning than it was produced in the end. Now, apply what we've just learned to these homework questions, and please have them ready for tomorrow.